In this lecture, I'm going to be talking a little bit about the fundamental theorem of calculus. So to get us started, we want to talk about what's called the area function. Remember that when we started talking about derivatives, we talked about how the derivative represents a slope function, in that what the derivative can tell us is the slope of our function f at a point x. So as I let x vary, I can talk about f prime representing the slope of f at any point x and think about it as a slope function. So with area here, I can also have a similar idea. So if I have some function f that's continuous on an interval from a to b, then I can talk about the area function from a to some point x. So we know that if we're looking at the area under this curve f, from a to b, we've talked about how we can find that area using the limit of Riemann sums of rectangles. And that would represent a number, the actual area. But if we think about x varying between a and b, then we can look at how the area changes as x changes, or as x, I guess, moves between a and b. So we can talk about this function g of x, where g of x is equal to the integral from a to x of f of t dt. So we've got the area from a to x giving us the value of g of x. So when x is here, we have a value. When x moves to here, it grows a little bit larger. When x is here, we get a larger area. So we can think of the area function. So now this is a function, and for particular values of x, it would be a number, but I can also talk about the graph of g of x because it is a function just like f is a function. Our interpretation of this integral, again, is the net area of the region bounded by our graph of f and the t-axis on the interval from a to x. And we say net area because we know that sometimes our function can go both above and below the x-axis. So I can talk about, for example, in this case here, let's say I had the integral from a to x and my function f was this curve here. Okay, so the integral from a to x would be the area of this region up here minus the area down here. Okay. Well, as for that particular value of x, and as x changes, the value of the net area would also change. So let's see how this looks for a particular example. So what I have here is a graph of f. So this is y equals, we're going to call it f of t, because we're letting the endpoint here vary. So when we talk about this area function, g of x is the integral from 0 to x. Okay, so if I wanted to talk about, for example, g of 0, this would be the integral from 0 to 0 of f of t dt. And we know the integral from a starting point to the same ending point is equal to 0. If I wanted to compute g of 1, I'd be looking at the integral from 0 to 1 of f of t dt. So our independent variable here, 1, is getting plugged into that upper limit. So the value of g of 1 is the integral from 0 to 1 of f of t dt, which is this piece here. So that integral is 1/2 base times height. So we have a value of 1/2 for g of 1. Okay. Remember, g of x is this function, but we can compute values of g at various points. If we look at g of 2 is the integral from 0 to 2 of f of t dt. So it would represent this region plus, I'm going to say plus this region, except we know this region is below the x-axis, so it has negative area. So if I look at this, what I would have is 1/2 my base times height minus 1/2 base times height of this triangular area that lies below the x-axis. So this actually has value 0. Okay, so the integral from 0 to 2 ends up being 0 because this area above cancels out with this area below my t-axis. If I look at g of 3, I know g of 3 is the integral from 0 to 3 of f of t dt. So I see I'm looking at those two blue pieces plus this one. So I know that using my integration properties from earlier, this is really the integral from 0 to 2 of f of t dt plus the integral from 2 to 3 of f of t dt. So I really only have to figure out what this additional piece is. And I know that that's negative 1/2. So I'm going to have 0 minus a half, or negative a half, as the value of g of 3. G of 4 is going to be the integral from 0 to 4, or the integral from 0 to 3 of f of t dt, plus the integral from 3 to 4 of f of t dt. So it's going to be negative a half plus what I have from 3 to 4. So that's plus this piece. So I see that I'm going to be adding a half, so g of 4 is also going to be 0. G of 5 should be my integral from 0 to 4 of 0, plus my integral from 4 to 5 of f of t dt. So I see the integral from 4 to 5 is a half, so g of 5 is going to be a half. Let's see here. Oops, no, I'm going to have a little bit more than that, because I didn't shade in the right piece. So actually from g to 5, I have this whole region here. So the area of this triangle is 2 times 2, so that's divided by 2. So that's an area of 2. These two pieces cancel, so I've got 2 minus a half. So that's value of 3 halves. Okay. If we look at finding g of 6, I'm running out of room, I'll go up here. G of 6 is going to be this whole big blue triangle here above, plus this one that's above, minus these two ones that are below. So I'm going to have what I had for g of 5, plus the integral from 5 to 6. So that will be this blue square here with area 1, plus this one, plus this. So that's plus 2.5, or 5 halves. So we get 8 halves, or 4. So g of 6 is 4. G of 7, which this is telling us that we should estimate, we can't find it exactly because there's a curve here, but I know that g of 7 is going to be g of 6, which is 4, plus some of this area. So it looks like I'm going to have about 1 plus, looks like about 1 plus maybe a little bit, so we'll say maybe plus 2.25. So we can say 6.25 is our value of g of 7. Okay, so we see that g is changing as t changes, and I'll be able to talk about, once I have a little bit more information from this section, how I could actually go about sketching a graph of g of x. Okay, so before we state the fundamental theorem of calculus, or the first part of the fundamental theorem of calculus, which will give us some idea of the relationship between derivatives and this area function, I want to just work with a little example. So in this example, I've got a function f of t, which equals t plus 5, and I want to find the function g of x, the area function, which is equal to the integral from negative 5 to x, f of t, using geometry. So my curve f of t, which in the previous example was this pink line here, was my curve f. So here f is just this line, so it intersects the x-axis at negative 5 and the y-axis at 5. And g of x represents this area under this curve y equals f of t from negative 5 to x. So we have an area that looks kind of like this. So it's a triangular area. So I can talk about what the area formula for this integral is in terms of x. So I've got this base of the triangle, which is x minus negative 5, or in other words, x plus 5, and the height would be f of x, well, which turns out to also be x plus 5 in this case. So I see that the area would be 1/2 x plus 5 times x plus 5, or 1/2 x plus 5 squared. So one thing that I'm asked to consider in this problem is, what is g prime of x? So g prime of x, if g of x is this right here, would be 1/2 times 2 times x plus 5, which equals x plus 5. So one interesting fact that we notice here is that g prime of x turned out to be f of x. Okay, so this isn't a proof of what we're going to see next, but this is just an example that indicates that there might be a relationship between the derivative of our area function and the function that we're looking at, the area under. Okay, so here's where we get to state the first part of the fundamental theorem. This important calculus theorem says that if f is a continuous function on a closed interval, then the function g, defined as this area function, the integral from a to x of f of t dt for x between a and b, is a continuous function on the closed interval AB and a differentiable function on an open interval AB. Notice that because g has those two properties, several theorems that we've talked about earlier would apply to this function g. We could talk about a mean value theorem applied to this function, for example. The second part of this theorem says that, okay, g is a continuous and differentiable function. Its derivative is in fact equal to this function with x plugged in. It's actually equal to f of x. So we can write this as g prime of x, the derivative here, is equal to d dx of the integral from a to x of f of t dt is equal to f of x. So this gives some idea of the relationship between derivatives and integrals, and that the derivative can undo the integral in some way. Once we have the second part of the fundamental theorem, we'll be able to say a little bit more about ways we can think about this. But for now, we're going to practice applying this rule to some situations to show how we can take the derivative of the integral. This fact also means that our area function g, which is our area function of f, is an antiderivative of f. So we've got a connection here to antiderivatives. Okay. So we want to see what this looks like, how we apply this. Notice that the example that we did observed that in that previous case we did find that g prime of x was equal to f of x. And now we have this theorem that says this is actually always true as long as we're dealing with a continuous function f. Okay. So here we're going to apply this theorem to this example that we started looking at. We've got g of x to be this integral from 0 to x of f of t dt. And we want to try to identify where g has a maximum value and where it has a minimum value. So to do this, we have to look at g prime. So we know that to identify maxes and mins, we look at where g prime has critical values, or where g has critical values, which is where g prime is 0 or g prime doesn't exist. So notice that here we would apply the first part of the fundamental theorem. I would have to say that g prime of x is equal to f of x, and I know that this is the graph of y equals f of t. This is my graph of f, and I would look at this to identify my critical points of g. So notice that g prime of x is equal to 0 where f of x is equal to 0. So that's going to be at 1 and at 3. Okay, let's see, I guess it also hits at the endpoints. So if we go to make a sign chart here, we're going from 0 to 7, and we've got 1 and 3 on here. And this is for g prime, which is equal to f. So my sign of g prime between 0 and 1 is positive because f is positive there. Between 1 and 3, the sign is negative because f is negative. And between 3 and 7, the sign is positive. So this tells me that g is increasing, decreasing, and then increasing. So g has a max value at x equals 1. Or if we go back to what we had earlier, at the point 1 comma g of 1, or 1 comma a half, there's a max. Because earlier we found that g of 1 was equal to a half. G has a min value at x equals 3. So at the point 3 comma g of 3, and we found g of 3 to be negative a half. Okay. So I could also, even though this isn't strictly asking me for concavity, but I think I'd like us to go ahead and see where g is concave up and concave down, and then we could make a sketch. So if g prime is equal to f, then g double prime is equal to f prime of x. So let's see, f prime, I'd be looking at the slopes here. So I need to see where f prime would be 0 or does not exist. So I see that f prime doesn't exist at 2 because I've got a corner here, as well as at 6. So if I was going to make a sign chart for g double prime, I'd have 2 and 6 on here. This goes from 0 to 7. This is for g double prime, which means I'm looking at f prime. Between 0 and 2, my function f is decreasing, so f prime would be negative. Between 2 and 6, I'm increasing, so this would be positive. And between 6 to 7, I'm decreasing. So I see that g would be concave down, concave up, and then concave down. So using this information together with all those values that we found of g of 0, g of 1, g of 2, etc., I can sketch a graph of g. So I knew my values ranged from like 0 to a little bit more than 6. So I can put 1, 2, 3, 4, 5, 6 on here. And let's see, I went from 1 to 7. So I've got 1, 2, 3, 4, 5, 6, 7. We found that g of 0 was 0. So this is using previous information. G of 1 was a half. G of 2 was 0. G of 3 was negative a half. G of 4 was 0. G of 5 was, let's see, 3 halves. G of 6 was 4, so that came up here a little bit. And G of 7 was a little bit more than 6. And now I know that I'm going to be increasing, decreasing, and increasing, concave down, concave up, concave down. So we connect these points. We see we've got that max at 1. We've got that min at 3. And we've also got inflection points at 2, and I guess it's at 6, so I didn't draw this quite how it needed to be. This needs to go up and then start to go over a little bit. Let's see here. Oops, erased a little bit more than we wanted. So we've got its concave, oops, concave down, concave up, and then it starts to be concave down again at 6. I've got an inflection point here. Okay, so we see that what I have here, this is my g of x, it's representing my area function. So as the area changes, each point on this graph represents the area under my curve f up to the point x. Just like my derivative function could be treated as a slope function where each point on the derivative graph represented the slope to a point on the graph of f. Okay, so that's one application. We can also have these types of problems where I'm interested in computing the derivative of the integral, each of these two different integrals. Remember that the fundamental theorem says that the derivative of the integral from a to x of f of t dt is equal to f of x. So here, if I'm interested in taking h prime of x, the derivative of my integral is going to undo this integral, and it's going to make it 5 cosine squared x over 8x cubed plus 1. Okay, so what about this next one? Well, one of the things that we have to notice when we're applying this rule is it applies when I'm starting out at a constant and going up to this variable x. So there's something special about having the lower limit here be the constant 4, okay, and the upper limit here being my independent variable, in this case x. Okay, but here they're switched, so I have the integral from x to 0 of this dp over p squared plus 1. Notice that this also could be written, oops, as the integral from x to 0 of 1 over p squared plus 1 dp. Okay, so sometimes that differential could get moved if there was nothing in the numerator there. But if I want to apply this theorem here, I'm going to have to rearrange my limits of integration. So I would want to rewrite this as the integral from 0 to x of 1 over p squared plus 1 dx. But I know that when I switch the order of the limits of integration, I have to multiply by -1. So the integral from x to 0 of 1 over p squared plus 1 dp is equal to negative the integral from 0 to x of 1 over p squared plus 1 this should be dp. Okay, so now I'm ready to go ahead and apply the theorem. So now y prime is equal to negative, I can pull out that constant, remember taking the derivative of, this is a function here, the integral from 0 to x, so I've got a negative sign times a function. So negative is just a constant, so it's negative times the derivative of this, which is 1 over x squared plus 1. Okay, so these kinds of problems are pretty straightforward. We're just doing a straight application of this rule. There's one more twist that we can put on it. Let's say I wanted to take the derivative of something that looked like y equals the integral from a to g of x. So g of x might be x, or it might be some other function. Like you see in this next example, I've got an integral from 0 to x to the 4th, or I could have an integral from 1 to sine x, or from 2 to the natural log of x. So I could have some other function that's hanging out here in the upper limit. So how am I going to handle this? So there's a couple of notes that I want to make. Let's say that h of x is equal to the integral from a to x of f of t dt. Okay, so this is the sort of standard way of looking at it, except I'm just calling this h in this case. So I know that h prime of x would be equal to f of x. I could also talk about a function h of g of x, which would be equal to the integral from a to g of x of f of t dt. Okay, I could talk about plugging in a function g of x here, and that's the kind of thing that I have over here. So notice that y equals, according to one of these definitions that I've made over here, h of g of x. So it's a composition of functions. Well, how do we take the derivative of a composition of functions? We use the chain rule. So we can combine the fundamental theorem of calculus with the chain rule. So y prime here is h prime of g of x times g prime of x. Okay. Well, I know that h prime of x equals f of x. This is by FTC, the fundamental theorem of calculus. So h prime of g of x would be f of g of x times, and then I'd have times g prime of x. So whenever I have an integral from a number a up to some function of x of f of t dt, and I want to take the derivative will be f with g of x plugged in for t here times the derivative of g, by making use of the chain rule together with our fundamental theorem. So how would that look in this example? Well, I'd have y prime equals cosine squared x to the fourth times 4x cubed. So the derivative of my outside function uses the fundamental theorem, but then I have to also use the chain rule. Okay. Just to take one more example for practice, let's say that I wanted to take the derivative of the integral from 1 to sine x of t squared dt. The derivative of this would be sine squared x, so sine of x squared, times cosine x. Okay, so these are a lot of the really important concepts of the first fundamental theorem of calculus. We'll be talking more about the fundamental theorem and getting into part 2 of the fundamental theorem in class next week. Please let me know if you have any questions.